Okay, honors chemistry. This is the answers video for lesson 10, and it is on balancing equations. Also, a few questions on calculating atomic mass numbers. Okay, so let's go ahead. I'm going to do most of the problems for you. Some I'll leave for you, as I usually do. So let's go ahead and do number 1 right here. So there's two methods, the box method and the standard. I'd like you to do both of them. Eventually you want to use just the standard method of balancing. At first the box method is going to probably be a little bit easier, although it requires, a little more space and a little more writing. Okay, so I'm going to go ahead, I'm going to take this equation, ethylene plus oxygen produces carbon dioxide and water. Anytime you have a hydrocarbon or a carbohydrate that combusts with oxygen to produce carbon dioxide and water, it's a very common reaction. In chemistry, it's called a combustion reaction. It basically means something's burning. Okay, so this is what a machine of some sort would use to produce heat or light. Okay, so here we go. So what you do with the box method is you draw a box and you break out each of the elements into individual letters. So C2, I'm going to write C, C, and the H4, I'm going to write that as 4H atoms. This just helps you to count them, and that's the reason you do it. It seems like a lot of writing, but it just helps to count. The oxygen molecule, these are all molecules, by the way, they're all nonmetals, which are covalently bonded, so that creates a molecule, a separate independent structure that can move separately from other molecules. Okay, so oxygen is O, O, and then over here we have carbon dioxide. That's C, O, O, and then water. Okay, the idea is we need to end up, here's our line, so I can actually draw that down the middle to help just keep clear that you have to end up with the same number of C's on this side as on this side, the same number of O's on this side as on this side, and the same number of H's. You have to end up with the same number of atoms before and after the reaction. You're not going to create atoms. They're not going to appear or disappear. What you're simply doing in a chemical reaction is rearranging the atoms to form different compounds, new compounds. Oxygen is not a compound because it's O2, it's a pure element. I'm just making that distinction. The rest of these would be compounds because they have two or more different elements. Okay, so let's get going. So you can start with anything you want, but you want to avoid oxygen for two reasons. One is it appears in more than one location on the right side of the arrow. It could have been on the left side, but in this case it's on the right side. It appears in more than one of the compounds. It appears two different places. So you want to avoid that because it makes it complicated to balance. You save oxygen for the end. The other reason you avoid it is because you want to avoid pure elements at the beginning. Balancing oxygen, if you could do it, doesn't help you to balance carbon or hydrogen. So stay away from it for both of those reasons. Okay? And oxygen often is the element that will appear more than once on the same side of the arrow. Okay, so we can pick either carbon or hydrogen. Let's go ahead and pick carbon. There's one on this side, there's two on this side. So what you have to do is whichever one is the least, you add boxes until they're equal. So I'm going to add one more box over here. And even though I'm balancing carbon right now, you have to write the oxygens too. You can't just put a C over here. It has to be the entire compound of CO2. So I'm putting a second, what I'm effectively doing is putting a second molecule of carbon dioxide there, okay? So now when I look at it, I have two carbons on this side of the arrow and I have two on this side. So carbon is now in balance. All right, hydrogen. So hydrogen, I have two on this side, four on this side. So this is the side with the least. So now I'm going to balance hydrogen. And I'm going to go ahead and draw a box by adding a water molecule here, like that. So now I have 1, 2, 3, 4 on the right, and I started off, I already had 1, 2, 3, 4 on the left. So carbon is in balance, and hydrogen is in balance as well. So now oxygen, again, that's the one we saved to last. Now we have to deal with it. So let's see how many oxygen we have. We have on the left side 2, 1, 2. Over on the right we have 1, 2, 3, 4, 5, 6. So we need to add boxes on this side because it's the least until we have 6. So we're going to add another box of O2. That gives us 4. And now we need to add another box. And that gives us 6. Okay, so 2 carbons on this side, 2 on this side, 4 hydrogen on this side, 4 on this side, 6 oxygen on the right, 6 on the left. Everything's in balance. So now what you do is you just rewrite the equation. You can put the numbers up here. There's not really much space. So it's 1 box of C2H4. And I like you when you're first getting started with chemistry is to write the coefficient 1 even though you don't have to. Just like in math class, you don't have to. I'd like you to write it anyway because I want you to see these numeric relationships. Okay, plus 1, 2, 3 boxes of O2. So there's 3 O2. And that's going to produce 1, 2 boxes of CO2 and 2 water molecules. Okay, and that's the final answer. That's how you balance using the box method. Okay, let's go back. Now we're going to do it using just the standard method, which is what you ultimately want to get to, because this can take a lot of space, and you could end up with some of these that have 5, 6, 7, 8 molecules. You'd have to have that many boxes. It takes up a lot of space. And eventually you'll get to where, when you get good at it, you can do some equations, some chemical equations with in your head. Okay, what I'm going to do is put a little line, because what I'm going to do this time is I'm going to write the coefficients right up here in front of this. So we got O2, arrow, CO2, plus space. Again, I'm just leaving space for my coefficients, H2O. Okay, there we go. All right, so now what you do is you take each of the elements and you write them down here, C, H, O. And now you simply count atoms. So I have 2 carbon on this side, so I put a 2 there. And I have 1 carbon on this side, so I put a 1 there. Hydrogen, I have 4 on this side. I have 2 on this side. And oxygen, I have 2 on this side. And over on the right, I have 2 right here plus another 1 there. So 2 plus 1 is 3. All right, so now what you need to do is end up so these numbers are balanced. They have the same number of carbons on both sides. You have the same number of hydrogens on both sides. You have the same number of oxygens on both sides. So I'm going to again go ahead and start with carbon. There's 1 on this side, 2 on this side. So I'm going to put a coefficient. You cannot change the subscripts. You can't change these little numbers. They're stuck. Okay, what you can do is put a coefficient in front. Now let's be sure we know how to read this. This CO2 means there's 1 carbon atom and 2 oxygen atoms. Okay, and they're just put together into a molecule called carbon dioxide. Once I put a 2 coefficient out in front, I now have 2 molecules of CO2. So in total, I have 2 carbon atoms, and I have 2 times 2 is 4 oxygens. In other words, I started off, it's kind of what the box method showed us over here. I started off with 1 carbon and 2 oxygens, and now I just added a second carbon dioxide, so now I have another CO2. So now I have 2 carbons total and 1, 2, 3, 4 oxygen, okay? So you're really doing the same thing you did over here. It's just kind of a shorthand way to do it, and it's really the way you want to get to where you can do it. Okay, so carbon is now in balance. I'm going to basically, you want to keep track of things, so I'm going to make a 2 there. So now carbon is 2 and 2, so it's balanced. Now we'll go to hydrogen again. I have 4 on this side, 4 atoms, and the 4 only applies to hydrogen, not to the carbon. And I have 2 on this side too, so I'm going to put another 2 there. So now I have 4 atoms here, and I have 2 times 2 is 4 atoms of hydrogen there. So I'm going to cross this out and put a 4 there for hydrogen. And now at the same time I put the 2 there for hydrogen to make that 4, I also double the number of oxygens there. So the 2 is distributed to every element in that compound. So there's now 2 oxygen. So I'm going to change this. Now be careful. There's 4 oxygen here. 2 times 2 is 4, and there's 2 oxygen there. 2 times 1 is 2. So 4 plus 2 is going to give you 6. So I now have 6 oxygen. Stop for a second and think about that if that was a little confusing, okay? Again, this 2 distributes to that, so it's 2 times 2 is 4. This 2 distributes to the 1 right there that you don't write, so it's 2 times 1 is 2, so 4 plus 2 is 6. Okay, and so finally the only thing we need to do now is we need to get the oxygen in balance. We have 2 on this side, 6 on this side, so we're going to multiply this by 3. So 3 times 2 is 6, and now everything's in balance. 2, 2, 4, 4, 6, 6. So there's my coefficients. The reason I write them up above is because they may not be my final coefficients. I might have to change them again. So I write them up above. But now that we're done, we can go ahead. This didn't change. There's one C2H4. There's 3 O2s. I can scratch that out. There's 2 CO2s. I can scratch that out. And there's 2 H2Os. And I can scratch that out. And you can see that we got the same answer that we got down here. Okay, so it's a way to check your work. You should get the same answer both times. All right, here's another hydrocarbon combustion reaction. So you see these 2 reactions look absolutely identical. What's not going to be identical is the way they balance. Okay, the coefficients are not going to be the same, but the nature of the reaction being a combustion reaction, you can see it looks like the one above. Okay, so let's go ahead and draw our boxes. And notice the H2O is in first position here on the right with the CO2 second. It doesn't matter. So just want to make that point. Up above it was the CO2 and then the H2. It does not matter. Okay, there we go. Just check to be sure you drew the right number in each box. And now you're ready to get started. Let's start with hydrogen this time. So we have 2 here and we have 6 over here. So we need 3 more boxes to create 6 hydrogen. Okay, so hydrogen is in balance, 6 and 6 on each side. All right, carbon, we have 2 on this side and 1 on this side, so we're going to need 1 more box for carbon dioxide. So 2 carbon and 2 carbon, so everything there is in balance. Now we just need to count our oxygen. And we have 1, 2, 3, 4, 5, 6, 7. Okay, think about that. What do we have we need to have 7 here? Okay. So I'm going to draw a box like this. There's 6. Uh-oh, I can't draw another box because those there. I can't draw another full box because 2 more would give us 8. We only want 7. This side has 7. We need 7 on this side. But you're not allowed to do that. You're not allowed to just break an oxygen molecule into just an oxygen atom like that. So how do we solve that problem? Okay. So what we have to do is, you're not allowed to have just a half a box. You just can't do it. You can't break these boxes up like that. I already told you that. So what do we do? Well, here's what we do. We're going to draw the other half box. But I really can't do that. So I'm going to have to add 3 more boxes like this. Really? Really? Okay, so now I have 1, 2, 3, 4, 5, 6, 7 full boxes. That's a total of 14 oxygen. Okay. And since I doubled the number of boxes that I have here, I'm going to have to double everything else. So I'm going to come over here and draw a CC and another H, H, H. Okay. So if, again, I really had this many to put it in balance. I had 3.5. In order to have a full box, I had to just double it to make another 3.5, so a total of 7. If I double this, I'm going to have to double everything here, here, and here. So I just doubled that. Now I'm going to have to draw 3 more. I have 3 here. I'm going to have to draw 3 more. Oh my gosh, it's a lot of writing. This is the one situation where the box method may not be easier. And then I have 2 here, I need 2 more. If I doubled this one, I have to double everybody else. Because when I did this and drew 3.5, it was in balance. Everything was in balance at that point. The problem is that you're not allowed to do that, so I had to double it to get this one right. That means I have to double everybody else, okay? I want to be sure that's clear. Okay, so I did. I doubled everybody. So let's count. I have 6 and 6 is 12 hydrogen, and here I have 2, 4, 6, 8, 10, 12 hydrogen. So hydrogen's in balance. Carbon, I have 1, 2, 3, 4, and over here at CO2 I have 1, 2, 3, 4. So carbon's in balance. Oxygen, we already counted those. I have 14. 7 times 2 is 14. So let's count. 1, 2, 3, 4, 5, 6, 8, 10, 12, 14. So everything's in balance. So what I end up with here is 2 of these, 7 of these, 1, 2, 3, 4, 5, 6 of these, and 1, 2, 3, 4 CO2s. And everything's in balance. Same number of atoms of each element on the left as on the right. Okay, that's what we just verified by counting them there. Okay, all right. Now let's do this the standard method. You might even say this is easier in this case to do it with the standard method. So let's give that a shot. So I'm going to rewrite. Okay, so I'm going to rewrite the equation. Okay, there you go. All right, so now what we're going to do is just write the elements down below the arrows. So CHO, it doesn't matter what order you put them in, just put them in some order. Okay, and we're going to count. We have 2 carbon on this side, and we have 1 on this side. Hydrogen, we have 6 on this side, and 2 on this side. And oxygen, we have 2 right there. And we have, again, just like last time, 1, 2, 3. So the starting numbers are the same as, well, I take that back. Not for carbon, it's not the same. Not for hydrogen, rather, it's not the same. Okay, so again, start with whatever you want. So we're going to start with carbon this time. So we're going to put a 2 there. It's just like we did before. And that's going to change this to a 2. So now carbon is in balance, 2 and 2. Okay. All right, hydrogen. We have 2 on this side, 6 on this side. So we're going to multiply this by 3. So we're going to put a 3 there. So now I have 6 hydrogen there and 6 there. So carbon and hydrogen are both in balance. Okay, now what we're going to do is, how many oxygen do we have? By the way, I didn't change the oxygen as I went along. I should have done that. So 2 times 2 is 4, and 3 times 1 is 3. So again, 1 oxygen times 3 is 3. 2 times 2 is 4. 3 plus 4 is 7. So I'll go ahead and just change that now. Okay, so now you have to ask yourself a little math question. I have 7 on this side and 2 on this side. What do I have to multiply 2 by so that it's equal to 7? And what you can simply do is, I'll come down here and do it down here. So 2 times what number equals 7? Let's just call it, instead of question marks, just call it x, just like math class, right? 2 times x, except the time sign looks like an x, so I'm just going to call it 2x. 2 times what? I'll put a dot, how's that? 2 times what number equals 7? So you divide both sides by 2, cancel, and x equals 7/2. Make sure you can see that. X equals 7/2, just math class. Okay, so I'm going to come up here and put a 7/2 here. So 7/2 times 2 is going to give us 7. All right? So now everything's in balance. The problem is you can't have, that 7/2 is equal to 3.5. You can't have 3.5 oxygen molecules. That's what we had down here, 1, 2, 3.5. So what we're going to do is over here is what we did over here. You're going to just double everything. Instead of 3.5 to 3.5, I'm going to double it and put another 3.5 to make it 7. But what did I effectively do? I doubled this. That means I had to double this, this, and this. So instead of 1, which is your coefficient there, 7/2, 3, and 2, I'm going to make this 2. I'm going to double that. I'm going to double this. So 2 times 7/2 is 7. Now I can scratch that out. 2 times 3 is 6. So I can scratch that out. And 2 times 2 is 4. And I can scratch that out. So 2, 7, 6, 4. And of course that's the same answer that we got down here. 2, 7, 2, 7, 6, 4. Same thing. Okay. It's not unusual in a combustion reaction. I won't say it happens most of the time that you'll end up with that kind of fractional situation with the O2. Just know how to deal with it when it happens. It's not that tricky. It's little basic math, and that's it. Okay? All right. Okay, let's move on to number 3, and we are going to do it. I'll first go ahead and do it using the standard method, and then we'll go to the box method. So let's count our atoms. 2 on the left and 1 Fe on the right. Oxygen. Oops. 3 plus 1. Okay, so watch out for that. There's 3 here. There's 1 more here. Again, everything on the left side. That's 4. Over here is a 2. And carbon, we have 1 and 1. Carbon's already in balance. Okay. All right, so what are we going to do? Well, there's 2 things I said to avoid at first. One is a lone element. There's a lone element. And the other is anything that appears more than once on the same side of the arrow. And oxygen does that, as it often does. So if I had to choose one of those, I would say still avoid the oxygen. The appearing twice just makes the problem a little more complicated. So I'm going to go ahead and balance the Fe. The carbon's already in balance, so there's nothing to do there. So I'm going to balance Fe. I'm going to put a 2 there. And that balances with the 2 there. So let me change that to a 2. So the only thing that's out of balance is oxygen. Now it looks like it might be kind of simple. There's a 4 there, there's a 2 there. The problem is we have 2 oxygens here. Okay. So here's one thing. This one's going to be a little tricky to do, so I'm just going to show you how I'm going to approach this. I have 4 oxygens on this side. I have 2 on this side. I know that whatever coefficient I put in front of this, it has to be the same for this. Why? Because the carbon are already in balance. And so if I put a 2 here, I have to put a 2 here. If I put a 3 here, I have to put a 3 there. That way the carbon stays in balance. So I have to find a way that I don't throw the carbon out of balance, and yet allows me to balance the oxygen, which is the last element that's out of balance. So let me just do, again, whenever you have 2, it just makes it a little trickier. Let me just try putting a 2 here. If I put a 2 there, this has to be a 2. Again, because we got to keep the carbons in balance. Okay, so how many oxygen do we have on the left side of the arrow? We have 3. And then there's 2 times 1 is 2. 2 times 1 is 2 plus 3 is 5. So we have 5 on the left side. Over here we have 2 times 2 is 4. That's not in balance. That's not going to work. Okay, so let's go ahead and erase that. Let's try 3. Okay, so I'm going to put a 3 here, and if that's a 3, then this has to be a 3 in order to keep carbon in balance. So let's see what I have here now. I have 3 times 1 is 3, plus 3 more. So 3 plus 3 is 6 for oxygen on the left side. On the right side, it's 3 times 2 is 6. So that balances. So then this is the correct number, is 3. You kind of had to do a little trial and error there. So that means my coefficients here are going to be 1, 3, scratch that out, 2, and 3. Okay, and that takes care of that. That's how you do that. Now let's do it with the box method and see how that would work. Okay, all right, so let's see. So we're going to go ahead and draw a box here. Okay, so what are we going to balance? Let's go ahead and balance the Fe first. So Fe is in balance. Carbon's already in balance. Okay. So what we have to do now is we have 1, 2, 3, 4 oxygen on the left and 2 on the right. So since you have fewer on the right side of the arrow than on the left, we're going to draw another box here. Okay, so now we have 4 and 4 for oxygen on both sides. That's good. Unfortunately, we've thrown the carbon out of balance. We now have 2 there and only 1 over on this side. So we're going to have to draw another CO box. Okay, so carbon is now back in balance. All right, but oxygen, we have 4, 1, 2, 3, 4, and here we have 1, 2, 3, 4, 5. Okay, well, what are we going to do? Now, so we have 5 on this side, we have 4 on this side, so we've got to draw a box on the side that has the least, and that's this side. So now we have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, but we've thrown the carbon out of balance again. You see, this can go back and forth a couple of times. So we need 3 carbon on this side, we need 3 on this side, so we're going to go ahead and put another CO box. So carbon is back in balance, and as it turns out, oxygen is in balance as well. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So everybody's in balance, and that's it. So that would be 3 boxes here, 2 boxes here, 3 boxes here. Gives us the same answer in both places. This time definitely the box method was easier. This one you kind of had to do a little algebra problem in your head. So anyway, this one was easier for that. Okay, let's keep going. By the way, let's do this. What's the name of this compound? It's a metal and a nonmetal. Okay, see if you can name this compound. So it follows the naming rules for ionic bonds, because metal, nonmetal is an ionic bond. And remember, iron can have more than one possible charge. It could have a 2+ or a 3+. We don't know which one it is. But we know oxygen is a 2-. Okay, you get that, you just figure it out from looking at your periodic table or the charge ion periodic table. And we have 3 of them, so 3 times 2- is 6-. In order to charge balance, the iron has to be a 6+. So we have 2 times something is going to give us 6+. That would have to be a 3+. Okay, so let me say that again. We're not sure about the iron at first, but we know oxygen is a 2- charge, and we have 3 of them. So 3 times 2- is 6-. So we have a 6- charge for oxygen. The iron has to balance that with a 6+ charge, and we have 2 iron. Therefore, 2 times whatever that charge is has to equal 6. That means it has to be a 3+ iron. So the name of this would be iron. Now it's not the 2 that's the Roman numeral, it's the charge. Iron 3. Iron 3 oxide. In the oxygen with IDE, that's the name for that. Okay, so just a little more exercise on how to name compounds. Okay, what about this one? What's that called? This is a covalent bond, okay? Selenium, nonmetal, or at least it's in the nonmetal side of the periodic table. It is a covalent bond. So it's selenium hexachloride. Hex is 6, hexachloride, okay? All right, let's do this box method first. I'm going to have to draw a lot of CLs there. SE. Okay, there we go. Just double check, be sure I got everything right there. All right, again, let's see. There's nothing we really need to stay away from, but oxygen's already in balance, so we don't need to touch it. The chlorine, we have 6 on this side, we have 2 on this side, so we're going to draw. We need to create 6 over here. So now we have 6 chlorine here, 6 chlorine there, so that's in balance. The selenium was already in balance. The oxygen was already in balance. And so that's it. It's going to be okay, there it is. 1 of everything and 3 of this except the Cl2, and there's 3 of those. Okay, that's all you do for that. Let's do it the other way. Okay, so there we go. So we're going to write the elements down below the arrow. All right, Se is 1 and 1, Cl is 6 and 2, O is 2 and 2. The only thing we need to balance is the chlorine. We're going to put a 3 there. 3 times 2 doesn't throw anything else out of balance. And that's it. So it's 1, 1, 1, 3. And that takes care of that. All right. Okay, let's keep going. Now, the last 2, I'm going to do one of the ways and you do the other. So you should always be trying to do these on your own. Yeah, always be trying to do them on your own, okay? Not just watching the answer, so get good at them. All right. So what do we got here? I'm going to do this one the standard way. And that's all the elements I have there. Okay, so let's count. Acetane has got 1, and over on this side there's 1 there, okay? Okay, sodium is 1, and sodium here is 3. O on this side is 1, and over on this side there's 3. And H over on this side is 1, and over on this side is 2. Okay, so you have 1 element already in balance. That does not mean that you might not throw it out of balance, however, during the balancing process, but then it eventually gets back into balance. Okay, so let's go ahead and let's start with hydrogen. So we're going to put a 2 up here. That's going to make this a 2. And that stays the same, so hydrogen is in balance. But what we also did is we made 2 oxygen. And we made 2 sodium. Okay, so we got hydrogen, acetane in balance. Okay, so what you got here is a situation where you, if you double the sodium on this side, make that a 2, then I'm going to have 6 sodium, 2 acetane, and 6 oxygen. Okay, so let's go ahead and do that. I'll put a 2 up there. So now I have 2 sodium. That's going to make 6 in all. So 6 sodium. And then I said 2 acetane. So again, you temporarily throw it out of balance. Okay, and then 2 O3s. That's going to make 6 there. All right. So now to get sodium and oxygen back in balance, let's start with sodium. Well, they're both going to be the same. You need to change this to a 6. So I'm going to change this to a 6 for sodium. Change this to a 6. So I have 6 sodium, sodium's in balance. 6 oxygen, oxygen's in balance. Now I have 6 hydrogen, so I got to change that. And now hydrogen is out of balance here, so to put it back in balance, I need to put a 3 there. So now that has 6. Okay? So 6, 6, 6, and 6, 2 times 3. 6 times 1 is 6. and 2 times 3 is 6 for oxygen. And for acetane, it's 2. Well, for hydrogen, I have 6 hydrogen, and I have 6 hydrogen. Acetane's the only one out of balance now. It's 2 there, but we can simply fix that by putting a 2 there. Okay, so it's 2 and 2. So everybody's in balance now. Let's just double check. 2 acetanes, 2 acetanes. 6 sodium, 2 times 3 is 6. 6 oxygen, 2 times 3 is 6. 6 hydrogen, 3 times 2 is 6. Everybody's in balance. I didn't leave space out in front to write this. I'll go ahead and write it down here. So, okay, there's the answer to that. Now I want you to rewrite the equation over here without the coefficients and do it with the box method, okay? Now notice you're going to end up with 6 boxes there. Okay, you already know the answer. So, but I want you to show the work, okay? That's required that you show the work. You can't just write the equation out. So show how the boxes work. Okay, and do that. Okay, this one down here I'm going to do with the box method, and you're going to do it the standard method. So here we go. Okay, so zinc's already in balance. Hydrogen 1 on that side, 2 on that side. Let's go ahead and balance hydrogen. So I have a second hydrogen. I also have to write the Cl. Okay, so I have 2 hydrogen, 2 hydrogen. I have 2 chlorines, 2 chlorines, 1 zinc, 1 zinc. Everything's in balance. So it's simply going to be, okay, 1, 2, 1, 1. Okay, so now you do it the standard way. Show your work. I want to see all the cancellations up there like that. Okay, don't just write an equation out. Okay, eventually we'll get past this and you can just do them in your head if you want. But for right now, while you're learning, you need to show work. Okay, now we're going to go on to a couple of atomic mass problems. I'm going to do one. You're going to do the second one. Okay, so an element named muonium, not a real element, has the following isotope masses and percentages. Again, how do you know what percentage is? You can't count massive numbers of atoms. So how do you know what the percentages are? You use mass spectrometry, and you can determine that, okay, of all the lines that are coming up, 94% of them are 46. 3%, 3.67 or 45, 1.98 or 47, 49. So this is the atomic mass units, the mass and atomic mass units for each of these isotopes. So the way we do this is, remember how you do a decimal. You slide, how you do a percentage. You slide the decimal over 2 places, and you fill that in with a 0 if there's nothing already there. So it's going to be this. Times the atomic mass of 45. So this is called a weighted average. Okay, so we're taking the percentage times that mass. That gives us 1.65. This percentage, make it a decimal, 0.9431 times 46. Gives us that number. 0.0198, again, move the decimal over 2 places. Times 47 gives us that, and then 0.00, so you got to move that decimal over 2 places, so it's 0.0004 times 49, and it gives us 0.0196. So now we add these numbers together, and that'll give us the atomic mass, and what we get for that is to 3 significant figures, because that's all we're working with on that number, and that number is 46.0, and we can call it atomic mass units. Or it could be grams when we get into molar mass, which we haven't talked about yet, okay? So that's the way you do it. Turn those into a decimal, multiply them by each of these. It's called a weighted average. You get a result, and then you simply add those results up to get your final atomic mass, the average mass of all the isotopes. Okay, I'm going to leave this one down here for you to do. Okay, and here's going to be your answer. So that's your check figure. You still have to show all the work, and you can do this on line paper as you wish, but you should show this work. This is really what I'm going to be checking, not that, because I gave you that. Okay, so be sure you show the work and do that correctly. Okay, and all those should add up to 75.2. That's 3 significant figures because that's all we have to work with those numbers right there. Okay, that takes care of it. So we will see you in class next week.